Good morning, Heswall. Yeah, Steve Barrett from the University of Liverpool. I'm a senior research fellow there. This isn't my area of research. I can tell you about that another day, perhaps. But I've always been interested in space, the universe, astronomy as a hobby. And this, I thought, was a good place to start. I wrote this talk many years ago about how the universe began. It has a companion talk because after giving this talk a few times to various groups, the questions at the end were, yeah, that's how it all started, but how will it all end? So that's a different talk, and I rather imaginatively call that one the end of everything. But here we've got the beginning of everything. I'm talking about giving a brief description of the origin and the very early history of the universe. So when we look out into the universe, what do we see? This looks like an artificial animation, a CGI, if you like. Well, it sort of is, but think of it more as a 3D atlas. We have mapped out the positions and distances to various galaxies, and therefore, when we plot them in 3D and do a fly-through, it's not showing up too well because of the sunshine coming through the windows, perhaps, but here's a fly-through of the universe, and we see that there are galaxies pretty much everywhere. But they are not uniformly distributed. They seem to be clumped together. Sometimes these clumps seem to form filaments. There seems to be a web-like structure. Some parts of the universe appear to be relatively empty. Other parts of the universe appear to be clustered with a number of different galaxies. But regardless of how they're all structured, there appears to be a lot of stuff out there. There appears to be, as best we can tell, hundreds of billions, perhaps a few trillion galaxies out there. Most of them probably have got hundreds of billions of stars. And as well as all of those stars and galaxies, we know that the universe is full of shed loads of dust and gas. And the question is, well, if there's loads of stuff out there, where did it all come from? Something like this, a Hubble Deep Field, reminds us just how much is out there. Remember, this is a tiny patch of sky, and yet we can see thousands of galaxies. That's how we come to the conclusion that probably throughout the entire observable universe, there are probably some trillion or so galaxies. But what I'm talking about is the creation of all this stuff that we can see. Where did it all come from in the first place? When did this happen? Well, we think about 13.8 billion years ago. The actual age of the universe depends to a little extent exactly what the model is by which we think the universe is evolving, but we'll see that shortly. We think the universe is 13.8 billion years old. How long did it take to make the universe in which we live? Approximately 3 minutes. That's all. 3 minutes makes everything in the universe. Everything after those 3 minutes has just been, well, just a little bit of rearrangement, basically. Where did it happen? Well, it happened everywhere because it's the beginning of everything. And if it's the beginning of everything, it can't have happened over there. It's the entire universe that we're talking about. So the creation of everything happened everywhere. Why did it evolve the way it did between its creation 13.8 billion years ago and the present day? Well, we believe it's evolved the way it has because of the laws of physics. How do we know all this? Same answer, because of the laws of physics. We believe the laws of physics can tell us about the nature of the universe's creation and how it's evolved to the present day. If we were to look at a game of chess, the question is, can we work out what the rules of the game are? It's a bit like saying if we look at the universe appears to be there. Can we figure out why? Can we figure out the rules of the game that allow us to say this is how the universe came to look the way it does? It's a bit like saying if I look at a chessboard, can I work out what the rules of the game are? If we have a look at an image like this, if I were to take a snapshot, if you didn't know anything about chess, and I told you this is a game of chess, can you figure out what the rules of chess are? The answer is probably no. At best, you might be able to say the pieces come in various shapes, but there appear to be two different colours, slightly different colours in this image. So maybe it's a game with two players. and it appears to be played out on this board of squares. Apart from that, you can't really glean anything else as to the rules of the game that dictate how you end up playing a game of chess. And you could say it's a similar problem with the universe. We can take a snapshot like this of a galaxy and we can say that looks very pretty, that looks very nice. But can we work out how that galaxy came to be the shape it is, or even the size it is, or the distance it is? Can we work out anything about how that galaxy came to be just by taking a picture of it? It's the same problem as the chessboard. No, we don't have enough information. If we could watch a movie of two people playing chess, then we could see how they move, we could see that they play alternately, we can see how the pieces move, and we can get a gist of some pieces are allowed to move in different ways to other pieces. We can figure out the rules of the game, perhaps if we were to watch a movie of a game being played. But we can't really do that with the universe, in the sense that we take a picture of a galaxy like that, and then if we take a picture of the galaxy tomorrow, it looks the same. And the day after, and the day after, and the day after, in 1,000 years' time, it will still look pretty much the same. Ideally, we would like to watch that galaxy for a few billion years, and then we can get an idea of what's going on and how it's changing and how it's interacting with other galaxies. But we haven't got the patience to sit here and watch it for a billion years. So what's the choice? Well, the choice is we could, in principle, not take a movie of a chess game being played, but take a picture of 1 million chess games, all at different stages of the game, or maybe 1 billion different chess games. If we could take snapshots of enough games of chess and see how it's developed in each of those games, we can get an idea of what the rules of the game are. Same is true of the universe. A picture of one star or one galaxy isn't going to tell us what's going on. But if we take a picture of enough, thousands or millions or billions of galaxies, some of these are at different distances, and therefore, because of the finite speed of light, we're looking back in time at various times. So some of these distant galaxies, we're seeing them as they were billions of years ago. Some of the nearer galaxies, we're seeing them in the much more recent past. So if we have enough data from enough galaxies, perhaps we can start to get an idea of what the rules of the game are. And rather than taking a Hubble picture, perhaps I thought ought to throw in a James Webb Space Telescope image, again showing us that even in a small patch of sky, there are huge numbers of galaxies out there. So there's no problem in that sense of getting large amounts of data. But when we look out into the universe, this is not the distant universe, this is just our backyard, this is just what's going on within our own Milky Way. It seems to be enormously complex. This is just a whole cloud of hydrogen and a few other elements mixed together. Those of you who are interested in astronomy might recognize the Horsehead Nebula, so this is part of the constellation of Orion. But when we look at this, we might think, well, it's crazy to think that we can work out what the rules of the game are when the result is such a complicated result. But we should remind ourselves that just because something looks complicated does not mean the underlying rules are beyond our comprehension. For instance, if we take a mathematical analogy, here's the Mandelbrot set, a collection of mathematical pixels. Here, the various pixels have been colored according to a mathematical formula. And there's maybe 1 million of them in this particular image. And this is not the entire Mandelbrot set. The entire Mandelbrot set, in principle, is infinite, and we can choose to display a certain part of it. If we zoom in, we see even more detail. At some point, it looks like maybe there's some things that are repeating, but actually these motifs that we see are not, strictly speaking, repeating. They are simply similar. In much the same way that a galaxy might have billions of stars, some of the stars might look similar, but they're not actually the same. And the same is true here. Nothing actually repeats. Every pixel is unique. So if we have an essentially infinite number of pixels that we need to color to produce this Mandelbrot set, how complicated must the mathematical rule be that allows us to generate each and every colored pixel of an essentially infinitely complex set of pixels? The answer is, the mathematics is that. That rule allows us to generate everything you see on the screen and a few billion times more than that, which I haven't got time to show you. So we should remind ourselves that just because something is incredibly complicated and complex, it does not mean the rules of the game that generated that system, that structure, are necessarily beyond our comprehension. One of my favorite quotes from Einstein is the idea that the most incomprehensible thing about the universe, or world if you prefer, is that it is comprehensible. The universe doesn't owe us anything, and yet, despite being monkeys who fell out of trees a million years ago, we are capable of looking out into the universe and getting a handle on how did it end up looking like this? What are the rules of the game? Just because it's complex does not mean it's incomprehensible. We just have to give it a little bit of thought. And that thought, roughly speaking, goes a little bit like this. We look out into the universe, we see lots of galaxies out there, each of which is made up of many, many billions of stars. The galaxies appear to be moving away from each other. So we come to the conclusion the universe appears to be expanding. And if it appears to be expanding, then we can always turn the clock back and say, well, everything used to be a lot closer together then. At the moment, the observable universe, everything we can see, everything we are able to see, is something like a sphere 100 billion light years across. But given that it's expanding, we can say, well, if you wind the clock back, everything used to be closer together. And there's nothing to stop in our imagination saying that if we take the clock back far enough, everything in the observable universe inside a sphere currently 100 billion light years across used to be only centimeters apart. Now, it's difficult to imagine everything in the observable universe being squashed into a golf ball. Well, okay, it depends on your imagination as much as anything. Particle physicists will do experiments and say to themselves, well, if you have particles with very high energy, which is presumably what would have happened if you take a large universe and think about running time backwards so that everything was much closer together. Presumably it was a lot hotter, a lot more energy, and therefore we can do particle physics experiments in which we can take particles, whether they be protons or something else, smash them together and ask ourselves what happens, what is matter made of? And let us assume that whatever we see here on Earth, it's the same everywhere else. Let's not assume that Earth is special. Let's not assume that the particles we see here on Earth are in any way different from the particles that are out there in the universe. And we have to make an assumption or two. We have to make the assumption that the laws of physics here on Earth are the same as the laws of physics everywhere else. It's not just a question of doing the same experiments and seeing the same particles. We have to assume the rules of the game are the same for everybody. If that wasn't the case, we would never make any progress whatsoever. If the laws of physics in England were different from the laws of physics in Australia, we would never get any progress whatsoever in understanding the world or the universe. We also have to assume that the laws of physics don't change with time, that the laws of physics now are the same as the laws of physics in the future and in the past. Again, if we determine the laws of physics now and they turn out to be different tomorrow, we haven't got any chance whatsoever of understanding anything. Therefore, we have to make this assumption to make any progress whatsoever. So we have to assume that the laws of physics are immutable. If they're not, then many of the conclusions we come to would be wrong, but this is the starting point because we can't make progress without these assumptions. Putting all that together, we come to the conclusion that the universe was created in a hot, dense state, a very compact state, 13.8 billion years ago, and it's been expanding and cooling ever since that point. And the question I'm trying to ask today is, when we look out into the universe and see all this stuff, all this matter, all these stars, all this gas, all this dust, where did it all come from? How far back in time can we go before we say, well, we think we understand the laws of physics, but I'm not altogether convinced that if we go back to the extreme early universe, I'm not altogether convinced we can still rely on our understanding of physics. How far back in time can we go towards this starting point 13.8 billion years ago? Can we go back to the first year of the existence of the universe? Yes, no problem. What about the first day? What about the first hour? What about the first minute? What about the first second? Yes, to the best of our knowledge, our understanding of the laws of physics is sound enough, is solid enough that we believe we've got a handle on that. What about the first fraction of a second? What about the first millisecond? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No. This is the point at which we have to say no. 1/1,000,000th of a second, 1 picosecond, 10 to the minus 12 seconds. From this point backwards, we don't really have a solid handle on what was actually going on. I'll explain shortly why 1 picosecond is the watershed between what we are reasonably happy with and what is pure speculation before that time. So before a picosecond, we're on shaky ground. We can speculate, we can come up with hypotheses, but in terms of our understanding of the theory, the Big Bang theory, that tells us effectively what happened from a picosecond onwards. In other words, everything from 1 picosecond to the present day, I would argue, is relatively well understood. And relative, of course, is a relative word. We don't understand everything, but we're on much better ground from 1 picosecond onwards compared to 1 picosecond backwards. So that was a very long introduction to what I'm actually talking about this morning, trying to lay down the sort of thought as to what it is we're actually trying to do. Before we now say, right, what happened in the first fraction of a second, the first few minutes of the universe, I need to just establish a few basic ideas, some of which you're familiar with and some of which you might not be familiar with. Once we got the few basic ideas out of the way on one slide, we'll then say, right, what happened in the first fraction of a second? What happened in the first few seconds? What happened in the first few minutes? And then, to avoid being here for the rest of eternity, we'll change speed somewhat and then say, right, what happened in the next 380,000 years? That's not a random number. There's a very particular reason for choosing that number. And then what happened in the next 13.8 billion years to get us up to the present day? So firstly, a few basic ideas. The first one, I hope, has come to no surprise for you. We are made of atoms. Put your hands up if you didn't know that. Okay, fine, yes. We are made of atoms. And an atom is a nucleus, a positively charged nucleus, and a whole load of negatively charged electrons buzzing around it. If we want to, we can take an atom and we can separate the nucleus from the electrons. We can effectively smash the atom, if you want to think of it that way. We can separate the electrons from the atom to leave us a whole load of negatively charged electrons and a positively charged nucleus. It takes a certain amount of energy to take an atom and to rip it apart into its constituent bits. An electron, to the best of our knowledge, is a fundamental particle. It's not made of anything else. You can't take an electron, cut it in half, have a look inside and say, what are electrons made of? As far as we can tell, you cannot do that. It is a fundamental particle. However, a nucleus of an atom is not a fundamental particle. You can, in principle, look inside a nucleus. And you can basically find out that most nuclei, the nuclei of most atoms, are made up of protons and neutrons. These are the names we give to the particles. We're not going to turn this into a particle physics lecture, but there are different types of particles within a nucleus, some of which have got an electrical charge, we call those protons, and some of which don't, we call those neutrons. Protons and neutrons, again, are not fundamental in the sense that you can have a look inside and ask, what are these things made of? And it turns out they're made of, well, we're made of things that we call quarks. Quarks, again, are fundamental. As far as we can tell, a quark is a particle, and you can't take a quark, cut it in half, have a look inside, and see what they are made of. At least we do not have any technology to do that, and we don't believe they are made of anything. I've said that 3 quarks make up a proton. The same is true for neutrons, but I'm just giving you an example here. You get this idea that this is a Russian doll sort of idea. Molecules are made of atoms. We can separate molecules into atoms. We can separate atoms into nuclei and electrons. We can separate nuclei. We can separate the contents of protons. But it takes more and more and more energy to go from the top of this diagram to the bottom. In other words, if we wanted to separate atoms into their constituents, it doesn't take much energy to do that. But we need relatively large accelerators if we want to start separating these smaller objects. So there's an implied energy scale from low energy at the top to high energy at the bottom. Now, to a physicist, if you've got a whole load of things washing around, a whole load of particles mushing around with high energy, we would call that a high temperature system. And low energy would be low temperature. In other words, temperature is effectively just a measure of how much energy each of the various particles have in a particular system. If we have a whole load of electrons, a whole load of protons, a whole load of anything, a temperature is a measure of how much energy. So if it's low energy at the top and high energy in the bottom, that corresponds to low temperature at the top and high temperature at the bottom. But remember, we came to the conclusion that the universe is expanding and started off hot and is cooling as it expands. That means there's an implied time scale here, because hot is at the bottom and cold is at the top, and we said the universe starts hot and ends up cold. There's a timeline going from bottom to top. In other words, the universe was built from the bottom up. It was built by taking quarks to make protons, and then taking protons and neutrons to make nuclei, and then take nuclei to make atoms, then take atoms to make molecules, and then use those molecules to make us. One way of thinking of it is to say, as the universe starts hot and cools down, you can't immediately take 3 quarks and make a proton, because if the universe has got too much energy, those quarks won't make a proton. The proton will have so much energy, it'll just shake itself apart. And similarly, you have to wait until the universe is colder before you can have, for instance, nuclei and electrons to make atoms. If you try and put nuclei and atoms together whilst the universe is too hot, they will simply shake themselves apart, they'll have too much energy, and you'll end up back to square one. So things are made like a Russian doll from the inside out, or from the bottom up. Okay, having got those basic ideas out the way, let's actually go through as a function of time and see how the universe began. What actually happened at time t equals 0? Well, perhaps it's no surprise to say that science cannot provide a definitive answer. I told you earlier that we've got a pretty good idea of what happens from 1 picosecond onwards, but not what actually happened in that first 1/1,000,000th of a second. There are various conjectures, there are various hypotheses of what might have happened, but none of them can actually be proven. Now, we know from the weird world of the very, very small that I told you about last time, earlier in the year, quantum mechanics is pretty weird. And quantum mechanics allows things called quantum fluctuations. It allows you to borrow energy from nothing. Sounds like a complete and utter cheat, but quantum mechanics is indeed weird, and it appears to be, as far as we know, a correct description of reality. And we are allowed to borrow energy, and because E equals mc squared, if you borrow energy, you can make matter, and that means you can make something from nothing. It doesn't disobey any rules of physics as we understand them. Now, yes, it sounds weird, and everybody thinks it's a bit of a cheat, but yeah, you just have to live with the fact that quantum mechanics is like that. How big a fluctuation can you borrow? How much energy can you borrow? Well, how much energy you can borrow from nothing depends on how long you've got to pay it back. You can borrow a lot of energy for a short time, or vice versa. It's like borrowing money from the bank. If you borrow a lot of money and you only want to pay back a little bit of interest, you have to pay it back very quickly. If you only borrow a small amount of money from the bank, even with high interest rates, you can borrow that money for quite a while before you have to pay it back. So how much energy did we need to borrow from nothing in order to make a universe? Well, we don't know, but it's been estimated. If you look out into the universe, we see lots of stars and galaxies and matter out there. We can add up all of the matter energy that's out there, and we can add up all of the gravitational energy that's out there. All the matter energy is positive, all the gravitational energy is negative. When you add it all up, the answer seems to be roughly nothing. So if that's the case, maybe we've got plenty of time to pay back the loan. Usually you think of it, you can borrow energy as long as you pay it back before the universe notices. Maybe we've got a long time before the universe notices that we've borrowed energy from nothing. Yes, I agree that it doesn't sound right, but that's what the weird world of the very, very small is all about. So let's move forward to the point where we are now talking about 10 to the minus 35 seconds after the instant of creation. The universe has expanded from nothing up to the size of a golf ball. And when I say the universe, here I mean in the context of the observable universe. Everything that we now see in the observable universe in a sphere 100 billion light years across used to be contained in something about the size of a golf ball. Everything was only a few centimeters apart from everything else. And just like a golf ball, this is why I like this analogy, as well as being very compact and very dense, it has dimples. Golf balls have dimples in them. The universe had dimples in it back in the day. Now, not little dimples in the physical sense of little indentations on the surface. I mean dimples in the sense of small variations of density and temperature across the entire golf ball. When the universe expanded, when it was much, 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 much bigger, these dimples eventually gave rise to the density variations that we see in the universe. The fact that there's a galaxy over there but not over there is a density variation. The density variations were tiny in the original golf ball, but as the universe expanded, those density variations were exaggerated to the point where there's now nothing over there, but there's a galaxy over there. We'll see a simulation of that towards the end of the talk. We're now going forward 1 picosecond after the Big Bang. 1 picosecond after the universe's creation, the golf ball has now expanded until it's about the size of the solar system. Yes, I know the solar system doesn't exist yet, but just to give you an idea of scale. We've gone from something size of a golf ball to the size of the solar system, but it's only taken us that tiny fraction of a second. So clearly the universe has been expanding much, 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 much faster than the speed of light. That's perfectly okay. It's allowed to do that if it wants to. The temperature has now fallen to a mere 10 to the 15 Kelvin. That's a ridiculously high number to try and imagine, but it is something that can be calculated. And remember, that temperature is a measure of the average energy of all the constituents. We're imagining that we've borrowed energy from nothing and we've used it to make stuff. We've used it to make matter. We're actually going to be generating lots of fundamental particles. Let's just think of them as a bag full of quarks and electrons and probably other stuff. But just to keep it simple, let's just imagine it as a quark soup. It's a soup of particles that includes quarks and other particles, so let's just call it a quark soup. At this temperature, all of the elements in the quark soup, all of the particles in the quark soup, have an energy that's comparable to the energies that we can generate in the Large Hadron Collider. In other words, we can generate particles with energies equivalent to the energies 1 picosecond after the Big Bang. Hence, we can test our ideas. If we have an idea of what might be happening, we can say, well, let's actually find out what happens when quarks have this level of energy or protons have this level of energy. Because we can test our ideas in an accelerator here on Earth, that means we have a reasonably good idea of what's happening from this point onwards. Prior to this point, the energies were so high we couldn't reproduce the conditions on Earth. From this point onwards, we can. Therefore, if it's testable, we have a reasonable idea we're on the right track. Energy and matter are continually swapping backwards and forwards. We originally borrowed energy to make matter, but at this scale, energy and matter are continually going backwards and forwards. E equals mc squared tells us what the exchange rate is, but basically it means energy can make matter, matter can make energy. Originally, matter and antimatter are made in equal amounts. I don't know how to represent energy in a PowerPoint presentation, so I'm just going to use a capital E to mean a certain amount of energy. That energy can be used to make a quark and an antiquark, or an electron and an anti-electron. It can make matter and its antimatter equivalent. Antimatter being the partner of every particle of matter, looks the same except it has the opposite electrical charge. So energy can make something and its anti-something. Probably not a tangerine and its anti-tangerine, that's probably not what happens, but the point is it doesn't matter. It makes something, it makes a particle of something and its antiparticle, which then annihilate with each other to make energy, usually in the form of radiation. And that energy can then make another particle of matter and its antimatter. It's not going to generate the same one again necessarily. It could generate something completely different. Probably not a hot dog and an anti-hot dog, but that doesn't matter. It generates some particle of matter and its antimatter equivalent. And that is going on back and forth, energy to matter and antimatter, back to energy, back to matter and antimatter, back and forth and back and forth and back and forth. But somehow, via a mechanism we don't fully understand, matter gained a very small excess over antimatter. We think they should have been made in equal quantities, 50-50, but somehow there was an imbalance in that more matter than antimatter was created. And I've represented it here graphically by a whole load of matter and a whole load of antimatter. To make the graphics easy to see, I've assumed that the matter excess is about 10% or something. In other words, there's a 10% excess of matter over antimatter. It was nowhere near that big. It wasn't 1 part in 10, it was more like 1 part in a billion. But I can't represent that in a PowerPoint presentation here. So what happens if you make this amount of matter and antimatter? All of your particles of matter have an antimatter equivalent that they can annihilate with to make energy. And that is true of all of these particles of matter, except for the last one, which hasn't got an antimatter partner to annihilate with to make energy. So what we end up with, once everything has settled down, is a universe that's absolutely full of energy in the form of light, radiation, doesn't matter what wavelength we're talking about, electromagnetic radiation, and some matter. So all of that is the light we see in the universe, and that little bit of matter left over, that 1 part in a billion left over, is everything we see. Is every galaxy, every star, every speck of dust, every atom of gas in the entire observable universe is that little bit that's left over. And that, of course, includes the solar system and the Earth and us. So we're very grateful for the fact that there was an imbalance. If there was an antimatter equivalent there, then the universe would be full of light and nothing else. So it's just as well that imbalance did actually crop up. What happened in the first millisecond after the Big Bang? Matter and antimatter continuing to pop into and out of existence. Protons and neutrons can be made out of quarks. Quarks are fundamental particles. Let's not worry about why they've got such a silly name. They're fundamental particles, and when 3 of them get together in a certain way, I'm not going to start explaining colours, and I'm not going to start explaining what the hell U and D actually refer to. When 3 quarks happen to get together and look like that, we call that particle a proton. And when 3 quarks get together and they happen to look like that, we call that particle a neutron. Proton and neutron are just the labels we give to what happens when quarks get together in a particular way. A bag of 3 quarks looking like that is a proton. A bag of 3 quarks looking like that is a neutron. Because quarks are continually annihilating, generating energy, coming back to quarks again, not necessarily the same quark. Neutrons can turn into protons, protons can turn into neutrons, back and forth and back and forth and back and forth. During this first millisecond or so, protons and neutrons are changing into and out of each other continuously back and forth. After about a second or so, the universe has cooled down to the point where it's only about 1 billion Kelvin. Sounds quite hot. Okay, yeah, there are not many stars that are that hot, even at their core, but the universe has cooled to about 1 billion Kelvin. And at this point, the universe is too cold for protons and neutrons to readily go backwards and forwards. In other words, to readily swap back and forth. In principle, it's possible, but it's getting more and more difficult because there's less and less energy available for them to do that. If you can't any longer swap backwards and forwards between protons and neutrons, how many of each do you end up with when you start to tally and look at the spreadsheet of how much has the universe made? Well, it turns out, because protons are a little bit lighter than neutrons, how do we know that? Because we can measure it in the lab. Remember, we're assuming that whatever we can do, the laws of physics now are the same as the laws of physics billions of years ago. So if protons were lighter than neutrons now, they were lighter than neutrons billions of years ago. The difference is only about 1 part in 1,000, but that means that the universe ends up making more protons than neutrons. Here I'm representing it by a certain number of objects, of which 3/4 are red, they're the protons, and 1/4 are blue, they're the neutrons. Why do you end up making more protons? Well, nature always prefers the lower energy, or if you prefer, prefers the lower mass. One way of thinking of it is there's only a tiny difference in mass of these two particles, but if the protons are lighter, well, nature will make more of them because they're easier to make. It's only a small difference, but it's enough at this temperature to give us that difference. We can calculate using the laws of physics as we understand them. At this temperature, if there's this mass difference, what would be the ratio of protons to neutrons we end up with? And it turns out to be this particular number here, 12 of the protons versus 4 of the neutrons. We're now moving forward to approximately 2 or 3 minutes after the Big Bang. Neutrons, the blue ones, are unstable. How do we know that? Because we can measure it in the laboratory. And if they're unstable now, we assume that they were unstable when they were made billions of years ago. If neutrons are unstable, some of them will change spontaneously into protons. We know that happens. And so the ratio of red to blue changes from my previous diagram. Instead of 12 of one and 4 of the other, we now have 14 of one and 2 of the other, because 2 of the blues have now changed to reds. And the universe is now 100 million Kelvin. So it is now possible for nuclei to form, by which I mean that up till now the universe has been too hot for protons and neutrons to want to get together. If you try and force them together, they have so much energy they just separate again. But now the universe is cool enough at 100 million Kelvin for nuclei to form. And what protons and neutrons really, really, really want to do is make this structure here. This structure, which is 2 protons and 2 neutrons. It's called an alpha particle, or if you prefer, the nucleus of a helium atom. So 2 protons and 2 neutrons, if they get together, they make a very stable structure. And that's what they really want to do. But of course, if 2 neutrons and 2 protons get together, we're left with a whole load of bachelors who haven't got neutrons to marry up with because there's not enough of them. There's only 2 neutrons for every 14 protons. So we can generate one of these so-called alpha particles, or the nucleus of a helium atom, but we're then left with 12 bachelors. And these are protons which stay as protons because they can't marry up to make alpha particles, or nucleus of helium. And a single proton is simply the nucleus of a hydrogen atom. So at this point, roughly 2 or 3 minutes, let's say 3 minutes after the Big Bang, the relative abundance of hydrogen and helium is fixed. From this point onwards, you can't change that. Well, if you wait long enough, eventually stars will start fusing hydrogen into helium. But over the next few million years, this number has now been fixed. And if we look out into the universe and say, regardless of what stars are doing in terms of fusing hydrogen into helium, if we look at all the gas that's out there and ask ourselves what is the ratio of how much hydrogen to how much helium in all of the gas we can see in the universe, it turns out to be this ratio. By mass, 3/4 hydrogen to 1/4 helium. The fact that the Big Bang theory effectively gives us the correct ratio for how much hydrogen and how much helium, that is a good indication that Big Bang theory is a relatively sound hypothesis. Not so much a hypothesis anymore. It's now a theory because it's got so many explanations for what we see in terms of observations. It's gone from a possibility to effectively an acceptance amongst the consensus of scientists. Now that we have a universe which is full of hydrogen and helium and tiny amounts of other elements, but let's ignore those for the time being, nothing interesting happens for the next 380,000 years. In other words, the universe is continuing to expand, it's continuing to cool, but effectively it's just that mix of 3/4 hydrogen, 1/4 helium gas that just continues to expand for the next 1/3 of a million years or so. But something interesting happens at 380,000 years. The temperature drops until it gets to about 3,000 Kelvin or so. Why is that a particularly interesting temperature? Because that's the temperature at which it is possible for the nuclei, let's just take a single proton here for hydrogen. Up till now, the proton has been floating around on its own, and there's been a whole load of electrons flowing around it as well, negatively charged. But at this particular point, the temperature is low enough for a proton to hang on to an electron. Prior to this, the universe was too hot and they would shake themselves apart and the atom would ionize. But from this point onwards, it's possible for a proton to hang on to an electron, and hence it is possible for atoms to form. This is the first point in the universe, the first time in the universe, where atoms are able to exist. So the universe changes from a plasma, which is a whole load of positive charge and negative charge all zooming around separately. Now we have positively charged nuclei with negatively charged electrons buzzing around them, so electrically neutral atoms. And the consequence of that is the universe, for the first time ever, becomes transparent. Up to this point, the universe was opaque. It was a mush, a plasma of positive and negative, and light could effectively not get through this. It's like a ball bearing trying to go through a pinball machine. It was continually getting scattered off the positive and negative charges. But now the universe is transparent, it is possible for light to fly through the universe. At 3,000 Kelvin, the universe would have been essentially white hot. There would be huge amounts of ultraviolet and some visible light. That light we can see today, but bear in mind the universe has been stretched out since this point, 380,000 years after the Big Bang. The universe is now 1,000 times bigger than that. And so the light, which originally had a wavelength of order 1 micron or so, that's been stretched 1,000-fold by the expansion of the universe. So instead of being a micron or so in wavelength, it's now millimeters or so. The light is no longer visible light, it's now microwaves. And that is the cosmic microwave background. And that's the second strand of evidence that tells us maybe there's something real about this Big Bang theory, because not only does it predict the amount of helium in the universe, it predicts that we ought to be able to see a microwave background across the entire sky. When that was discovered in the 1960s, that was proof that, yep, the Big Bang theory appears to be absolutely the best theory to explain how the universe began. So this is the whole sky unwrapped into this ellipse. And it shows us that although there's a lot of microwaves coming from all directions of sky, this is exaggerated to show us there's slightly more in some directions and slightly less intensity of microwave radiation coming from other directions. In other words, there's a small temperature variation across the sky. And that is simply a consequence of the fact that the original golf ball had dimples in it. The golf ball had dimples in it, which is small variations of density and temperature, and we're seeing those small variations of temperature when we look at where the microwaves are coming from. So that's why it is rather important that when we look at the microwave and it looks relatively smooth, but we do see small variations, it's not perfectly smooth, those small variations are definitely worth studying in detail, because those map directly back to the dimples in the original cosmic golf ball, and hence the more we study, let's get some satellites up there to look at these microwaves in as much detail as possible, because by studying the microwave background, we are effectively studying the early universe. We can see a little simulation of how that might happen. Simulations allow us to start with not necessarily a golf ball, but start with a small chunk of the universe in which we've artificially put in some small variations of density and temperature, and let's watch gravity take hold and watch it collapse into what we hope is the universe we see today. So a simulation, we don't take a large sphere, we just take a cube of universe, fill it with matter, put in some small variations of density and temperature. Here the color blue is an indication of the density or the temperature. Lighter blue indicates hotter, denser regions. And this is a simulation. You can go and look at these videos yourself if you're interested. Here's the simulation running for a few billion years. As time goes by, gravity grabs hold of these small variations. The dense bits get even denser. the low density regions get even lower density. And you can see regions where these filaments are forming, and as the filaments meet, you get galaxies and clusters of galaxies and superclusters of galaxies forming. And you end up with something which looks a little bit like a filamentary web, which is called the cosmic web. And remember that 3D atlas I showed at the beginning of the talk. When we look out and ask ourselves, where are the galaxies? We don't find that they are uniformly distributed. We find some regions in which there's very few galaxies, and we see some regions in which galaxies appear to be lined up on these filaments as part of the cosmic web. So the fact that these simulations do allow us to start with an early universe, let gravity do its stuff, and we find that we end up with a large-scale structure of the universe which looks reasonably similar to the actual structure we see when we look out into the universe, again gives some credence to the fact that maybe the Big Bang theory is the theory that does explain where everything came from. If we look at what's going on in a local structure, this is a sort of a map showing what's going on around the Milky Way. That's the Milky Way galaxy and one of our immediate neighbors, the Andromeda galaxy. Various small satellite galaxies, not all of which are shown here. There's many dozens, possibly hundreds of them, buzzing around in the so-called local group, this gravitationally bound region of galaxies encompassing us and some of our immediate neighbors. If we zoom out a bit, our local group is in the middle here, and we see that there are other clusters of galaxies not so far away, Virgo cluster, Fornax cluster, etc. And notice there are some regions which appear to be, well, for whatever reason, not many clusters up in the top left or maybe at the bottom there. If we zoom out again one more time, we see we're right in the middle there, there's a whole load of clusters, and we can see this mottled effect, which tells us that we have, on the largest scales, we have structures here, we have large areas that appear to be devoid of any galaxies, and we have galaxies and galaxy clusters which appear to be lined up in this filamentary structure. This void here, again, is a reminder that what we're effectively looking at, this mottling that we can see of where are all the galaxies in the universe, the mottling structure we can see is a consequence of the fact that the early cosmic golf ball had dimples in it. So what happens in the next 13.8 billion years? Well, essentially, if in 3 minutes we can understand where all the hydrogen comes from, well, if we've got shed loads of hydrogen, then we can start to say, well, yeah, okay, hydrogens make stars and stars turn hydrogen into heavier elements, etc. So once we've got the hydrogen, you could say, done deal. Now we understand galaxies and stars and planets. And we understand trees and mountains and snowflakes and rainbows and cats and, okay, probably not cats. I don't think we'll ever understand cats, but we basically understand everything. If we say, yeah, start with hydrogen, everything comes from that, that's a bit of a gross statement, but yeah, that's not far off the truth. I admit there are still some details of cosmic evolution we have yet to nail down, but at least we've dealt with the big one. How did it all start? Where did all the hydrogen come from? Once we've got the hydrogen, we can start to say, why did that galaxy form like that? Why is this star behaving the way it is, etc. So just a graphical reminder of what I've just been talking about, with a ridiculous time scale of 10 to the minus 35 seconds on the left and now on the right. So we don't know what happened in the very early universe, but basically it seems like we borrowed energy from nothing to make a whole load of quarks and electrons and other fundamental particles. After a minute or so, some of those particles got together to make bags of quarks, which we call protons and neutrons. After a minute or two, those protons and neutrons got together to form either helium, or anything left over is what we're calling hydrogen. And after 380,000 years, eventually electrons get in on the act to make neutral atoms. The universe turns transparent. The light flies across the universe, and that's what we see as the cosmic microwave background, 380,000 years after the Big Bang. What happens next? Well, we're not too sure. There's the Dark Ages. After the cosmic microwave background was released, it takes a little bit of time for the first stars to get their act together. In other words, for the hydrogen to condense from clouds into what we now call stars. Did it take 100 million years? Did it take 500 million years to make the first stars and make the first galaxies? That's one of the reasons the James Webb Space Telescope is up there, looking back as far as possible in time to try and figure out what happened in those first few 100 million years after the hydrogen was formed and available for stars to use. What were the first structures? How did black holes get in on the act? What was made first, black holes and then galaxies, or galaxies and then black holes? Once we start forming stars, we can start to ask questions about stellar evolution and what the universe looks like now. And of course, we now have a good idea of what's going on our backyard, and now we have a rough idea of the timeline that got us from the beginning of the universe all the way up to the present day. But I must admit, yes, the jigsaw is not actually complete. I have glossed over a few bits and pieces. Why did matter win over antimatter? It appears that must have happened because we are here. Everything we see around us is made of matter. The Earth, the solar system, the Milky Way galaxy, and as far as we can tell, every galaxy in the observable universe appears to be made of matter, not antimatter. So why the imbalance? Why the asymmetry? And I've been very careful, where possible, to talk about trying to understand the beginning of everything, where everything means everything that we can see. Everything we can see in terms of galaxies and stars and gas and dust. But there's more out there than just galaxies and stars and gas and dust. Dark matter seems to exist. It results in galaxies rotating at a speed which is a little bit surprising. It appears to be out there, but we don't know what it is. There's lots of people that are frantically trying to understand what dark matter is. Similarly for dark energy, something appears to be making the expansion of the universe accelerate. You might assume that gravity would make it slow down as it expands, but actually it appears to be speeding up. And we don't understand what dark energy is and why it's doing what it's doing. So yes, this talk is called The Beginning of Everything, but I've been careful to say the beginning of everything that we can see. Dark matter and dark energy we can't see. We can see about 5% of the universe. Dark energy and dark matter account for the other 95%. But they are still a bit of a mystery. But that's another story. Thank you all very much.